Standard pop science rankings usually focus on a linear countdown of the largest cosmic monsters discovered in deep space. This approach hides how these structures actually operate. When stacked solely by size, the raw numbers quickly lose all practical meaning for the viewer. Take Sagittarius A star. As the supermassive black hole at the center of the Milky Way, it contains a mass of 4.3 million suns, providing a local baseline for what massive looks like. At the opposite end of the spectrum is Phoenix A star. Current estimates place its upper limit mass at 100 billion suns. This matrix illustrates the statistical problem. The mathematical gulf between 4.3 million and 100 billion is so vast that placing them on the same list fails to provide any useful context. This creates scale fatigue. To the human brain, the difference between 60 billion and 100 billion solar masses is largely abstract, causing every entry to blend into a single concept of extreme size. Truly comprehending these anomalies require us to categorize them by their specific functional behavior, rather than simply their ranking on a list. We are abandoning the size countdown to evaluate these structures by how they act. Our framework uses two specific metrics: behavioral volatility, the violence of their feeding habits, and observability, the amount of tangible proof we have of their existence. This quadrant chart maps our study. The vertical axis tracks activity from quiet to violent, while the horizontal axis moves from theoretical models on the left to direct visual evidence on the right. Sorting the data this way allows you to match your own intellectual curiosity to the specific branch of physics you want to explore. Since engaging with astrophysics is an investment of mental bandwidth, this framework ensures you spend that energy on the right mystery. Our first category is the grounded observables, focusing on anomalies located within our observable cosmic neighborhood. Messier 87, or M87, is the primary example. It holds a mass of 6.5 billion suns and sits 55 million light-years away. Its relative proximity allowed the Event Horizon Telescope team to gather enough data for a massive scientific breakthrough in 2019. They captured this, the first ever real photograph of a black hole. This blurry orange ring provides the direct visual proof that separates this category from more abstract theories. Because M87 is highly observable, we can also see its physical impact on the surrounding galaxy, most notably through its relativistic plasma jet. This image shows the jet itself, a beam of plasma shooting 5,000 light-years into space, driven by the black hole's immense power. Studying these local giants allows for the certainty of proven data, even if it means sacrificing the extreme scale of more distant monsters. The next category, the active devourers, maps high on the volatility axis of our framework. SMSSJ 2157 represents the extreme end of this scale. With a mass of 34 billion suns, it consumes the equivalent of one entire sun every single day. This process, known as accretion, creates a feeding frenzy of friction that generates massive amounts of heat and radiation. The consequences are visible on a galactic level. Anomaly 4C plus 74.13 once released a massive energy outburst after accreting the mass of 600 million suns. The massive shockwaves from that single event were powerful enough to physically reshape the entire architecture of the host galaxy. In this bucket, the black hole itself remains hidden. Your investment is spent studying the violent, transformative environment its feeding creates. Finally, we have the theoretical limit breakers. These objects are so massive and distant that they exist primarily on the far left edge of our observability chart. We measure TOM 618. Located 18.2 billion light-years away, indirectly. Its mass of 66 billion suns is calculated based on the brightness of its surrounding quasar, which outshines 140 trillion suns. These structures create a mathematical conflict. They represent more mass than current models can account for in the time elapsed since the Big Bang. Phoenix A star represents the absolute peak of this category, with a mind-melting estimated mass of 100 billion suns. According to the known laws of physics, this is the absolute theoretical limit of how large a black hole can physically grow. This extreme size creates a physical paradox. The event horizon is so vast that falling in wouldn't immediately trigger gravitational shredding. you would simply drift into a massive, featureless cathedral of darkness. The trade-off for studying these giants is a loss of observational certainty. You must rely entirely on abstract math and theoretical limits. The data reveals a consistent correlation. As these objects grow in theoretical mass, they move further away and become harder to verify. This final scorecard helps you choose your path based on 3 specific research profiles. Casual stargazers should invest their time in M87 and Sagittarius A star for tangible, localized data. Systems thinkers and sci-fi writers should focus on SMSS J2157 and 4C plus 74.13 to see the physical impact of galactic-scale destruction. Deep physics enthusiasts should dive into Phoenix A star to explore the boundaries where our current gravity models break down. Ultimately, the choice comes down to which specific mystery you have the courage and the tools to comprehend.